Hello. Okay, this is the second part. What we are discussing? We are discussing the zero dispersion wavelength. So the zero dispersion wavelength is the wavelength where the dispersion is changed from from one particular mode to the other particular. Say for example, normal mode to anomalous mode. So here for this silica fiber, the red one around 1.3, it is the zero dispersion wavelength. So there are many proposals to manipulate dispersion in the fiber, and accordingly different type of fibers have been invented. First one is dispersion shifted fibers, DSF. In this fiber, the zero dispersion wavelength is shifted to minimum fiber loss region in order to obtain both low dispersion and low loss. So low dispersion is important for for effective propagation of a pulse into the fiber, and also low loss will give you high efficiency. So zero dispersion shifted fibers have been investigated, and what they have scientists are able to do, they have designed the fiber in such a way that the the zero dispersion wavelength falls at the minimum level of the loss, okay, loss parameter. So as we have seen in the previous classes that how the loss has been uh, developed, low loss have been developed step by step after the this in advent of this optical fiber. And what is the communication window? We know that at around this communication window at around 1.55 micrometer, the loss is very almost small. That is for of the silica fiber. So in that fiber, if we able to take this dispersion, zero dispersion wavelength within that limit of 1.5 to 1.6 micrometer limit, where our optical communication window is there. So if we able to do that, then that will be calling as dispersion shifted fibers. So the fibers can be designed in such a way that we can have this dispersion shifted. Dispersion can be shifted to that particular region of the wavelength. So if that's so, then we'll be having an effective pulse propagation fibers. So next part is dispersion compensating fiber. In these fibers, group velocity dispersion is shifted to the lambda less than 1.6 micron wavelength region, and exhibit beta 2 is larger, much larger than 0, much positive. If beta 2 positive, then it will be normal dispersion, and if we have normal dispersion, then we must have the GVD, group velocity dispersion, beyond 1.6, sorry, yeah, lambda should be beyond more than 1.6 micrometer. If we take lambda equal to 1.6, above 1.6 micrometer, what will happen? If we 6 above 1.6 micrometer, then beta 2 will be negative, then that will be an anomalous dispersion. Beta 2 is positive. Oh yes, dispersion compensating. Yeah, if GVD is shifted to lambda greater than 1.6, if somehow we can make this graph beyond this 1.6, such that beyond 1.6 micrometer also we can have beta 2 very positive, then we can manage a lot of things, okay. So that part is called dispersion compensating fiber. So we can compensate the dispersion here uh, by making a GVD positive, a GVD beta 2 positive at even at lambda is greater than 1.6 micrometer. Okay, that is the dispersion compensating fiber. Now dispersion flattened fiber. This usually multi-cladded fiber. So low dispersion over relatively wide wavelength region, lambda equal to 1.3 to 1.6 micrometer. Okay. Dispersion flattened fiber means if we able to flatten this graph like this. Let me control 2. Yes. If we have a graph like this is very flat graph, okay, of dispersion. If we somehow able to get this kind of graph, here you can see this green color graph is having a very steep slope, and all other graphs have very steep slope. If we somehow able to minimize this steepness, and then our quality of our pulses which will be propagating through this optical fiber will be enhancing. So that is another important thing uh, in optical fiber. Okay, so last one is the dispersion decreasing fiber. In this case, dispersion parameter defined by this term, and accordingly group velocity dispersion varies or decrease along with the fiber length. This can be achieved by changing the core diameter with the length. So core diameter, by changing this core diameter, we can have here, let us consider this yeah, this, say for example, this is the core of the fiber. If we change this core diameter of this core, then our dispersion will be changing, and that will be also called that is called here the dispersion decreasing fiber. So dispersion can be decreased here. So this way we can change have the different kind of fiber with different kind of dispersion, manage dispersion. And the dispersion is important. If you have a very low dispersion at around at its zero dispersion wavelength, then it will be giving us the better effect of this one, the pulse. Because if dispersion is small, around to zero dispersion wavelength, then our pulse will be not broadened enough, and there will be large effect of the non-linearity. Okay, so it is better to have almost zero dispersion near the zero dispersion wavelength, minimize dispersion around the zero dispersion wavelength. So how we can do that? We can do by these uh, four processes. Okay, polarization mode is not required. Fiber non-linearities. Let's coming to the fiber non-linearities here. Okay. Okay. Today, now we are coming to the fiber non-linearities. We know how that when electromagnetic field falling in a dielectric in case of nonlinear dielectric response can be observed. Say for example, as we studied in our nonlinear class, when light pulse, when electromagnetic wave propagates through a nonlinear dispersion medium, then the polarization will be generated, and that polarization will be having the effect of the susceptibility and the electric field. And there is a constant permittivity, vacuum permittivity. So this when the high order nonlinear terms are there, then it will be this chi will be having several high order susceptibility terms, like chi1 is first order nonlinearity, chi2 second order nonlinearity, chi3 third order nonlinearity. Actually these are the susceptibilities, and susceptibilities are giving us the nonlinear effect. So the polarization will be having this first order, second order, third order nonlinear effect embedded here if the electric field strength will be very high. Now we know this the chi1 is called the linear susceptibility, and this this quantity depends on the refractive index n and the attenuation coefficient alpha. Chi2 is the quadratic or second order susceptibility. This part is present only in the media which is having lack of inversion symmetry in molecular level. That part we have rigorously discussed in the third semester. And the lowest order nonlinearities can be attributed to the effect of the third order susceptibility Chi3, leading to such phenomena such as nonlinear refraction, third harmonic generation, four-wave mixing, etc. etc. This Chi3 is responsible for self-phase modulation, modulation instability, soliton generation, etc. Four-wave mixing, all those things are coming because of this Chi3. Okay, so this these are the fiber nonlinearities. First one is linear linear part of this susceptibility. Chi2 is second order nonlinearity which is absent in the media, which is having inversion symmetry. Chi3 is the third order susceptibility or third order nonlinearity, and that will be our that will be giving us a lot of nonlinear phenomena, including nonlinear refraction, third harmonic generation, four-wave mixing, soliton generation, etc. etc. So next topic is nonlinear refraction. In this part, but we know this equation very well. This equation is nonlinear refractive index, and this is attributed by two terms. One is the linear refractive index, another is nonlinear refractive index. So the phenomena which shows the intensity dependence of the refractive index is caused by third order susceptibility. The effective index of the fiber mode is n equal to n is a function of omega n I. Intensity and frequency is given by n is a function of frequency, and n2i. Here n2 n has a linear dependence of on the frequency, and the nonlinear part proportional to the intensity, optical intensity. The nonlinear index coefficient n2 is related to Chi3, and this relation is called as the Carr effect. And from this effect we come to know that this n2 is having a relation with Chi3, and by this relation, and this n0 is the refractive index at the central frequency of the optical pulse. We can say it this is the linear refractive index. Okay? Now the intensity dependent refractive index leads to two important phenomena: self-phase modulation and cross-phase modulation. What is happening in self-phase modulation? As an ultrafast pulse travels in a medium, it induces a varying refractive index. In exchange, it produces a phase shift in the pulse. Its magnitude can be calculated as phi equal to n plus n2i k naught l. Now here, this is the concept of self-phase modulation. What is there in the self-phase modulation? When a pulse, an optical pulse, which is ultra fast, means very fast optical pulse of, say for example, a nanosecond pulse. When it propagates to an optical medium, which that medium should be nonlinear as well as dispersive, and it produces a varying refractive index. Means if we can see, okay, see, say for example, this is the pulse. Okay, this is a pulse having same, consider this is having same frequency, but if self-phase modulation, that self-phase modulation is introduced by this nonlinear refractive index. Here you can see phi, there, that is a phase shift which is attributed by this nonlinear refractive index, and if that is there, then there will be a change of phase.